and upload the lecture notes. But before uploading, I want people to read it carefully so that see whatever is in the video, some error here and there done in the class cannot be corrected. But it can be backed up by a lecture notes which does not have any typos or anything like that. So I would request that go through that carefully and bring out any. Already a few good ones have been pointed out by Inzamam, but I expect more careful also reading. Okay. All right. What I will do today is almost complete the real number construction. A few things I will mention. So let's recall. We had Z, we had Q. From Z we went to Q, from Q we went to R. Okay. And then we got the arithmetic, the plus here induced the plus on the rational numbers, which induced the plus on the real numbers. So basically it is a genetic plus that was there with the integers which got carried over slowly to the level of real numbers. Then we had into among the integers, and that induced the into onto the real numbers. So basically we are only working with the integers in different formats, a little bit more fellows being generated out of them. Okay. And all these are therefore the addition that we have on the rational numbers is in a sense a hereditary property. It got from it the previous generation. And the addition that we had on the real numbers is a hereditary property which it got from its predecessor, the rational numbers. Similarly, the multiplication in Q is hereditary, got it from the predecessor, and the multiplication in R is again hereditary, it got it from the predecessor, the rational numbers. And then we had the order greater than in Z, two numbers, real numbers, we say either they are equal, they are greater, or etc. The order induced an order here which induced as an order here. So again the order is a sort of a hereditary property. Okay, so all these have been passed on from generation to generation. In fact, you can go back to one more generation to the positive integers, that is the natural numbers, and then construct the integers. So that is again a sort of a hereditary thing that will be moving on, some of these things. And of course, a generation earlier, and to start with the integers, we need the positive integers, we need the Peano's axioms. Okay, so that's where everything starts. All right, we'll not go that far back. We assume that we know these things. Whenever it's needed, we'll bring them up. Okay, then we had this that made Q plus into a field. The addition and the multiplication that Q got from the previous generation made it a field, but the field property is not hereditary. The previous generation, the integer was not a field because multiplicative inverses were not available. So this is not hereditary. If you have gone through a simple definition course in abstract algebra, this is only what is known as the integral domain. Okay. But now When Q became a field, the R becoming a field was only hereditary. Okay, so this R plus into is a field and that is hereditary. Okay. Nowadays nobody worries about spelling because you can type any spelling and then put through a spell check. We'll take care of it. But I always get confused with the spelling wherever there is an I or something like that. It is H-E-R-E. Okay. And sometimes the Americans would even pronounce it as hereditary. You start thinking it is a T-O-R-A or something like that. So I think I got the correct spelling. It is T-A-R-Y. Okay. Alright. So some of the properties are hereditary. Now this one is extra got by removing defect in Z. That's how the construction of the rational numbers started. That multiplicative inverse did not exist. So equations Ax, M or Nx equal to D could not be solved. And from then on we moved to remove that defect and that gave us the rational numbers. And then this had a defect. Okay, let me before going through that. And now this order is hereditary. So finally we get this is an ordered field. And this is also an ordered field. So we'll make a little comment a little later about these ordered fields. Okay. I will make about the defect removal from Q to R shortly. That aspect of it was the construction from Q to R. I'll make a comment. But before that, one more comment. I had said Q, R. Now, Z has a property called Archimedean property. I think there is no point in giving names for these properties because they are all so old and so many people have mentioned. I don't know why it is called Archimedean. I'm sure somebody before Archimedes also would have known it. And maybe in those days they didn't publish it and so on and so forth. But anyway, if you don't know, if you think that it is before so many people, you say it is Archimedean. Okay. It's 250 BC or something like that. So take care of as far back as you can think of. The property is this. Suppose I have two integers, m and n, both are positive and m greater than m. Okay. So I have two positive integers and m is greater than n. So though n is small, if you go on taking several copies of n, eventually you will beat m. So in other words, you have $1 million, I have $1. But I go on making dollars, after some time I will beat you. That's what the Archimedean property is. That is, implies there exists a positive integer n such that if you take n copies of that smaller quantity, that will beat the bigger quantity. N times n is greater than m. So that is the Archimedean property. Now, using the construction of Q from Z, we can easily see, I mean the definitions are all there. This is a nice exercise to do, that this Archimedean property in Z induces a corresponding Archimedean property in Q. So this induces Archimedean in Q. What does that say? If xy belong to Q, and x is greater than y greater than 0. Exactly replica, except now instead of m and n being integers, we take m and n being rational numbers. Implies there exists a positive integer n such that if you take sufficient number of copies of y, it will beat x. Okay. And this in turn induces Archimedean property in R. What is Archimedean property in R? If R and S is consistent to be notation, R greater than S greater than 0, then there exists a positive integer n such that n times S will beat R. Okay. So now a drop of water and an ocean, several drops of water will beat the ocean. If you take sufficient number of drops of water, it will beat the ocean. That's what the theorem is. Okay, that's what that Archimedean property is. So once you have Archimedes, you have to talk something about water. Okay. So, all right. So far so good. So everything looks nice. We have been going along, removing defect, carrying the old property, acquiring new properties, and moving along, etc. Then finally we had that Q had a defect. What was the defect? Cauchy sequences in Q need not converge in Q. Our construction of R, the whole ballgame that we went through, was for the very purpose of removing this defect. So, we proposed our construction of R to remove this defect. Have we achieved it? So if we have achieved it, what should have happened? Every Cauchy sequence in R must have converged. So for that we must define what is meant by Cauchy sequence in R and then prove that every Cauchy sequence will have a limit in R. Okay. So towards that end, so we first define Cauchy sequence in R. Now I'll state it, I am slightly modified later. Okay. Today, okay. All the things I will not prove, particularly this one. This one should have been proved, but I think it's a messy thing to write. Better to read it in a book and get your notations done by yourself. So there are so many indices, you have to manipulate with everything. So first of all, I have Rk a Cauchy sequence of, a sequence of real numbers. Now, what is meant by a sequence of real numbers? Every real number itself is an equivalence class of sequences of Cauchy sequences of rational numbers. So, we should write Rk is equal to Rkn, where for each k, Rkn is a Cauchy sequence of rational numbers. This is the notation we had, CQ. For each k, Rkn is a Cauchy sequence of rational numbers. So now you see there are so many things. For each one of them, you have to choose, and then for each equivalence choice also, you must show the results are true. So there is a messy notation that will have to be worked out. So we'll just state the theorem itself. Okay. So then we say, let me first, Rk is, I'll just intuitively, okay, Cauchy sequence of real numbers. If for every epsilon positive, I'm going to leave some space here, there exists a positive integer n epsilon, that so that beyond that stage you go and see the difference between the real numbers will be less than epsilon. So such that n and m greater than or equal to n epsilon implies mod Rk, sorry, k and l, Rk minus Rl is less than epsilon. You go and see beyond a certain stage in that real number sequence. So the real numbers are here, R1, R2, etc. Then what it says, there is a stage n epsilon. I hope you can see that. Then if you choose an Rk and an Rl here, then the difference between them will be less than epsilon. Now we have to see what is meant by Rk minus Rl is less than epsilon. Rk is an equivalence class, Rl is an equivalence class, so the difference is the difference equivalence class and modulus is the modulus equivalence class. So what it really means is, that is mod less than epsilon. Okay. To make, so I said I leave some gap here. What is that gap? I will take epsilon in Q, a rational number positive. You may object, Mrs. In the real number situation, I say epsilon to be real. Why are you taking? First of all, let me make it for rational numbers and then explain that that's enough. Okay, a little later. One property I will state. Okay. What does this mean? This means, I should write what? Rkn, Rln, because each Rk is a sequence, Rl is a sequence of rational numbers. That is the equivalence class, because Rk is Rkn, Rl is Rln, so that is the difference sequence, Rkn minus Rln. So this is, so the right hand side is also a real number, but now it's a rational number also. So you can think of it as the real number sequence epsilon, 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 epsilon. Now what is the difference? What is the meaning by saying this is less than epsilon? Beyond a certain stage, this will be less than epsilon. Beyond what stage? Now which is the stage? N is the stage now. So there will be a positive integer n which will depend on the k and the l, such that beyond that set Rkn minus Rln will be less than epsilon. There exists, that is, there exists a positive integer n which will depend on k and l, such that nm or n greater than equal to nkl implies mod Rkn, I should have put mod Rkn minus Rln is less than epsilon. So that's, let me rewrite that definition. Given any epsilon rational number, first of all there is a positive integer that depends on that rational number, and such that if you choose a k and l beyond that positive integer, there is another positive integer which depends on that k and l, such that beyond that stage Rkn minus Rln will be less than epsilon. So what is the formal definition? Let's write it. It's said to be a Cauchy sequence. So let me rewrite it again. So this is the formal definition. Rk sequence of, let me write it, Rk equal to Rkn is a sequence of real numbers it is said to be a Cauchy sequence if for every epsilon positive epsilon in Q there exists an n epsilon such that for every k and l greater than or equal to n epsilon there corresponds a positive integer nkl such that n greater than or equal to nkl implies modulus of Rkn minus Rln is less than epsilon. Did I write it? Rkn. That's the, so what we do is first of all go beyond a certain stage, pick these fellows, then write the sequences corresponding to them, take the difference, you get a new sequence. In that sequence you go beyond a certain stage, the difference will be less than epsilon. So we have, we can explain what this is. We have R1, then I choose, there is a positive, this is the positive integer n epsilon. Beyond that, I choose Rk and Rl. Okay, k and l greater than or equal to n epsilon. Now I am going to write the sequence corresponding to this Rk1, Rk2, etc., Rkn, and then the sequence corresponding to this, etc. Then take the difference which is Rk1 minus Rl1 and in general this, and look at, okay, let me even write it carefully. So I look at the corresponding difference sequence and then in that I put a barrier nkl, then I choose Rkn minus Rln. That n is beyond that stage. That will be less than epsilon. So first move these fellows, then come down, move these fellows, then the difference is less than epsilon. So there are two sequences you are handling. First handle the real sequence, then fix the stage, then having fixed the stage, take the two fellows in that stage, then look at the rational sequence corresponding to them, take the difference, and then look at a stage at which it becomes less than epsilon. So there is a double indexing that you will have to take care of. And the theorem is, once you have a Cauchy sequence, it will converge. This is a theorem which is the completeness theorem of the real line. So what I will do is I will just take, this is the most important theorem, okay. Theorem, every Cauchy sequence in R converges in R. That is, okay, let me just write that. You know what the meaning is. So therefore, we have removed the defect. If we prove this theorem, because I am not going to prove this theorem, but this theorem will tell us that we have indeed removed the defect that we really wanted to remove. Okay, so no longer Cauchy sequences have problems. Cauchy sequences will definitely converge. Okay, and of course, therefore, we can state a result here. Therefore, Rk, a sequence of real numbers, is convergent if and only if it is a Cauchy sequence. Now, if it is convergent, is a Cauchy sequence, is the same proof as we did in rational numbers. Now we are having an extra thing. If it is Cauchy sequence, it will be convergent. So in real number, they are synonymous. Cauchy, being a Cauchy sequence and being convergent, they are synonymous. But this is not true in rational numbers. So this is not a hereditary property. This has been acquired by the extra construction effort that we did. Okay. So we have indeed achieved it, that we have removed the defect. I will state one more property. I think if you, best thing is whenever you are traveling in a train or a bus is difficult. Nowadays buses are also good. Take one of these things and try it to see how we can prove it. That will tell you whether you really understood the construction and everything that has gone on. The property is this. Suppose Rs or any two real numbers are not equal to S. Okay. Suppose I take two different real numbers. Okay. Then there exists a rational number Q such that it lies between the two real numbers. Those two real numbers may be rational. This also tells between any two rationals there is a rational. But it also tells between any two reals there is a rational. Between any two real numbers there is always a rational number. So this is a very important property which will be repeatedly used in analysis. Between any two real numbers. Actually you have to see the proof of what is meant by greater or less in our Cauchy sequences and then see how things work. Okay, I will leave it. So basically what it says is Rn stays to the left of Sn, the sequences. So somewhere in between I will put an Rn plus Sn by 2, but properly to be chosen. Okay. Okay, now therefore it didn't matter, I could have put an epsilon R also, because if I wanted to make it less than a real number, make it less than a rational number which is below it. That number between 0 and epsilon, 0 is a real number, epsilon is a real number, so there will be a q in between. So I will make it less than q. If it is less than q, it is also less than epsilon. So in that definition, I could have put epsilon as R also. So most of the time when we prove, we are not really going to prove epsilon. We will always be looking at some numbers of the form 1 by k. If I will make it less than 1 by k for every k, I can make it less than epsilon for any epsilon. Okay, that's the idea. Okay, in most of the proofs. Okay, that's called the density property of the rational numbers. I'll probably not prove at the moment. Okay. So these are two crucial theorems, but for lack of time, I don't want to get too much involved in. I want to get to real functions, theory functions, and the topological properties of the. This is a fundamental topological property. Between any two real numbers, there is a rational number. Okay, I will explain what these all mean. But before I do that, I want to briefly, for half an hour, maybe 10 minutes, describe another person, Dedekind, who looked at real numbers in a different manner. So he constructed his own system and he called it real numbers. Then there is a confusion. Cauchy constructed something, we constructed something through Cauchy sequences, we call that also real number system. Dedekind constructed something, he calls also the real number system, which is really real number system. And both are same. In the sense that we are talking about the same thing in different languages. Like you may say ek or other fellow may say one. Okay, so that's all the difference. So you have to have a dictionary to translate. While translating the dictionary, we can identify the numbers Addition will be identified, multiplication will be identified, order will be identified, Archimedean property will be identified, everything will be identified. So it is the same thing. One fellow is called talk Dedekind language, another fellow is talking Cauchy language. That's all. That's all the fundamental. So I will describe Dedekind. Okay, I am not going to do the details. I will just point out what exactly he does. Lot of proofs have to be done, but I'm not going to do all that proof. Okay. I'm not even going to probably in the class discuss how addition and multiplication is defined, but maybe I'll just at least put the definition on the notes, okay, for you to, for anybody interested in. Now the idea is the following. What Dedekind does is, here is the rational numbers, and everybody starts with the rational numbers, okay. Cauchy also starts with rational numbers, then he looks at Cauchy sequences and goes through that, and Dedekind also starts with rational numbers, but he does something different. What does he do? He splits the rational numbers into two different groups, okay. So let's start with Q. I don't want to put a line yet, I'll put the line and explain to you, okay. Then split Q into two pieces which we call as L and R. Say such that you will see why I use the notation L and R, though R is a bad notation because you want to use R for real numbers, but most people use LU, but I like to see LR. Where, how is the splitting done? First of all, these fellows are non-empty. Okay. I have split them into two parts, means their union is Q. That is, it's a partition. It's a partition of the rational numbers. So I put some rational numbers in one bag, I put the remaining rational numbers in another bag, and this bag I call as L, this bag I call as R. I make sure I put something in each bag. They are non-empty bags. But the important thing is these 2 points. L belongs to L, R belongs to R, implies L is less than R. What does that mean? The L bag always stays to the left of the R bag. That's why the right and the left. Okay. R is the right bag, L is the left bag. Every element of L bag stays to the left of every element of the right bag. Okay. And most crucially, L does not have a maximum or a maximum. That is no largest element. Let us explain this description first. Okay. So L is one collection of rational numbers. R is another collection of rational numbers. They are disjoint. I'm sorry. Because this itself says they are disjoint. Anyway, I'll write it. Everybody is less than R, so there cannot be anybody common. Okay. So if somebody is common, he is less than himself, which is false. Okay. Anyway, to make sure that there is a partition, I'll write it as L intersection or SMT. So I have these two bags. Everybody in this bag is smaller than everybody in this bag. This fellow does not have a maximum. That fellow may have a minimum or may not have a minimum. So let's look at some examples. Okay. One such. So let R example. Let R, or what should I say? Let be any rational number. Take any rational number Q. Okay. Then let L be the set of all x in Q such that x is less than R. And R be the set of all x in Q such that x is greater than R. I will call it as LR and RR because they depend on R. Right? That's obviously a partition, and the left side back does not have a maximum because whatever rational number you give smaller than R, I can find one more. The average between the two will be still there. So the L doesn't have a maximum, but now R has a minimum, smallest element. Okay. So this is a valid such partition, LR, RR. Okay. I will denote it by LU. So such a cut, such a thing is called a Dedekind cut. Such a thing is called a Dedekind cut of Q. So LU, and we denote it by LU. L is the left class, LR. See, I almost go to the standard, see, brainwashed by the standard notation. LR. So therefore, this is a Dedekind cut. In this cut, R has a minimum, the smallest element, namely R. I'll give you another example. So every real number gives rise to, every rational number gives rise to a corresponding Dedekind cut. Okay, so therefore, every rational number R gives rise to a unique Dedekind cut dr equal to LR RR. It's unique because if you change the number R, then the left class differs from the right class. The left classes are different and the right classes are different. So every rational number gives rise to a Dedekind cut, and that's unique. Now let's look at another example. Again, I am going to partition Q. The way I partition Q is now slightly different. L to be the set of all x in Q such that x is less than or equal to 0, all the negative rational numbers union all x in Q such that x is greater than 0 and x squared is less than 2. Okay? So what is R? Only the remaining thing. The set of all x in Q so that x is positive and less than or equal. X is positive, 0 is gone there, and x squared is greater than or equal to. Now you see that R now does not have a minimum element because square root of 2 is not a rational number. In other words, there is no rational number such that x squared is equal to 2. There is no rational number x such that x squared is equal to 2. So LR is a Dedekind cut in which Obviously, every x is in L, every L in L less than in R. Okay. These are all negative. These are all positive. In which R also has no minimum. Has no minimum. Okay. So that's what is called a Dedekind cut. A Dedekind cut partitions the rational numbers into two parts, and the left part and the right part. The left part has no maximum. The right part may or may not have a minimum. Everybody in the left part is smaller than everybody else in the right part. That's the Dedekind cut. Okay. Now we see that whereas the rational numbers gave Dedekind cut, there are other cuts also which do not correspond to any Dedekind cut corresponding to a rational number. So there are Dedekind cuts corresponding to rational numbers. There are Dedekind cuts corresponding to numbers which are not rational. So therefore the cuts seem to be giving new numbers. Okay. So that is like you are having the real line. Whenever there is a gap, try to pull it up. All the fellows on the left side, all the fellows on the right side fellows don't have a minimum, the left fellows don't have a maximum. So what happened to the joining point? Okay, that joining point is a hole. It's a black hole in the rational number system, and that has to be removed, and therefore I put a number there. Okay, that is where the real numbers start coming in. So what Dedekind said is, take the collection of all such cuts, all possible cuts, and that is my real number system. Okay. So Dedekind said is, let D this is more geometric in nature. When you see, draw the picture and see everybody on this side, everybody on this side, what happens to that joining point? If he is there, it's a rational number. If he is not there, it's a new number. Okay. Let D be the collection of all Dedekind cuts of Q. All the Dedekind cuts of Q. All possible Dedekind cuts. Okay. All possible Dedekind cuts of Q. D, okay, note every R in Q is identified with a unique Dedekind cut dr equal to Lr Rr. Therefore, we call it as phi r. So therefore, we can identify the rational numbers inside the D. So therefore, Q can be identified with phi Q in D. For every R, there is a phi R, and that's unique. So therefore, we have these Dedekind cuts. We have the set of all Dedekind cuts, and we have the Q, and then we define a map R to phi R, and that is the range of phi, that is equal to phi Q. So the Q has been identified as a part of D. So but there are other things also. We have seen example 2, there are Dedekind cuts which do not come from rational number. So there are things outside, and therefore we have a bigger number system. This is called, the Dedekind called this as the real number system. We will call this this as RD. This is the real number system constructed by Dedekind. The other one I should have called it RC, the real number system constructed by Cauchy, but I'll just call it as R. So now Dedekind has his work cut out. Okay, he has to define addition, he has to define multiplication, etc., etc., and he does all that in a very natural way. Okay, it's almost it tells you what to do. The definition tells you what to do, and he cleverly does addition, does multiplication, and then does the order, and then shows that this is an ordered field, and therefore Dedekind has. So then Dedekind defines plus into greater into, all induced by plus into greater in kith. See, that has to come as hereditary, and because it's going as hereditary to the same gene which is working in a different language in Dedekind cut, and the same gene Q working in the Cauchy language, well, the expression of that gene must be the same, and it turns out that the two systems are the same. Okay, they're only the language in which they're expressing are different. They're isomorphic. Okay, just like a biologist may say the two protein structures are isomorphic, it's exactly these are isomorphic. Okay, then we showed RD plus into greater is an ordered field. Okay, that's the general idea of what. Of course, only one. This has to be done carefully. I'll give the definition of plus, into, and greater in the notes. I'll put it in the notes instead of writing it in a messy manner. There are fairly natural definitions. See, now by this time you get used to what it is. If you want to define many times high school students ask me, why is it minus into minus is plus? Okay, it is all built into this construction and the definitions. Okay, and how does it come in? They are all naturally coming into this definition. So one has to, if you always give them some very phony answers, because you can't give them this construction, how the real numbers have been created and so on and so forth, and give them something which, because if you try to, then they are lost. So give some answer which looks convincing and so on and so forth, but one has to go to really the construction of the real numbers. Okay, and what Dedekind does is, plus is very easy to define. When I want to define into, he says before that I will say what it means by something is positive and something is negative and something is zero. Then once I do that, I will define only the product of two positive cards, and once I define the product of two positive cards, then if I want to define the product of positive card with a negative card, because the plus has a negative, the positive card has a negative card, I will take the negative of the negative card, which is positive, and then go back to my positive cards, I get an answer and then negative it. See how it does is, x into minus y is minus of xy. xy is positive cut into positive cut, then negate it. Instead of negating it and then multiplying it, you multiply it and negate it, so it's already built in those properties in his definition. Similarly, when he says I have a negative cut and a negative cut, or a cut defining a negative number, another cut defining another negative number, if I want to multiply, what do? Take the negative and multiply, so that you are multiplying positive quantities, and just leave it at that. Okay, two negatives make it positive. This sort of arguments he puts forth, and so therefore he only says I will tell you how to multiply two positive cuts. and multiplication by anything should be 0 I want. That is because that is hereditary I want. So I will define it to be 0 and everything goes through. And because you see this is a hereditary property again. In rational numbers, positive into negative is negative. Where did that come from? It came from the integer. So basically it is all at the integer level these properties are all sticking around. Okay. Then this fundamental question, you have this Dedekind real number and the Cauchy real number. So which one should I work with? It doesn't matter. It is the same. You need a dictionary. So then there exists a field isomorphism F to R D plus into to this field. What is meant by field isomorphism? It is a 1-1 map. It's an isomorphism means 1-1 onto map. What is field isomorphism? It preserves the binary operations of the field. So if you take two fellows on this side and add and take the f of it, that is the same thing as telling take the f and then add. So you translate the sentence or you transliterate the sentence, both are going to be the sum. Word for word you translate or you translate the whole sentence. F of x plus y, the two words concatenated, is the same as then translate f of the concatenated word is equal to, now you take the first x translation and then the y translation, then put them together, you get the same. So translation and transliteration are going to be the same. That's what is meant by field isomorphism. Okay. And but it preserves the order. That preserves the order. That means if x is greater than y in Rd, then f of x is greater than f of y in the R. So everything is the same. One is the it is like one fellow is casting a shadow on this side. Instead of calculating here, you do the calculations on the shadow and then go back and forth you can do it. So basically they are the same. Okay, the one is the alter ego of the other. So really there is only one real number system. But thank God we have constructed only one real number system. Otherwise there will be two real analysis. Okay, even one itself is too much to take. Two real analysis would have been a little bit more difficult. Okay. So that is there is one more. This is the main thing. I will not get into other things. Cantor was too clever. I said I don't want all these things. I will tell you even how to construct integers, he said. I will tell you how to construct positive integers. Then you go to integers. Then you go to Q. Then so nothing is needed. I will do from simply magic. From nothing, everything can be created. But I will not get into all those philosophical questions. Okay. But still, in all these constructions, something must be given to us. The integers, or before that the positive integers, or before that the Peano's axiom. So somewhere, something you just are unable to create something from vacuum. But what Cantor said was, yes, give me vacuum, I will create something. Now I don't even know. So that is, you give me the empty set, I will create the positive integers, and therefore I will create the negative integers, and therefore I will create the rational numbers, and therefore I will create the real numbers. So something must be given. You give me vacuum, I will create everything out of it. So give me the empty set, everything can be created out of it. Okay. But still, somebody has to give him the empty set. Okay, the shunya has to be created. So somewhere along the line, we are stuck. You see, you just cannot create out of nothing. Okay. Though Cantor says I created out of nothing because the empty set had nothing. Okay. Right. So now next what I want to do, this is the construction of the real number system. The next chapter I want to do is the real topological properties of the real numbers, which and their generalization. So what I will do is simultaneously try to move you from real numbers to metric spaces. Parallelly, you can learn some of the general situations also. So which will allow you to go to n dimensions or complex numbers or matrices or anything for that matter. A large number of general classes we can move once you see what this is. So therefore, a crucial part in my movement are the following properties which I will state and quit. Okay. So suppose I take now the real numbers. For every r, we define mod r. Okay, we know how to define that. Okay, the absolute value of, how is absolute value of r defined? It is r if r is positive, minus r if r is less than 0, if r equal to 0, it is 0. So basically it looks at its size rather than the direction, which it is negative 4 or positive 4, it doesn't matter. It is 4, that's what is matters. Okay, that is what the absolute value is. Okay. Now, let me note. So what is this R to R? So it is a mapping. This is a mapping from R to R. For every real number, I associate another real number such that this is always positive. The value mod r is always positive, because when r is positive, I will take r as r. If r is negative, I take minus r, so it becomes positive. If r is 0, it's 0. So greater than or equal to 0. And the only case when it becomes 0 is r equal to 0. Equal to 0 if and only if r equal to 0. And then mod rs is mod r into mod rs, mod s for every rs in r. And the most crucial thing is try to prove this from the definition. Okay. Mod r plus s is less than or equal to mod r plus mod s. If all are positive, then one of them is positive, one of them is negative, both of them are negative. So all three cases you have to study and use this definition and see what happens. Okay. And whenever we write such thing, we want to see when equality take place. If and only if what? Both are positive, both r and s are greater than or equal to 0, or both r and s are, they have the same parity. In the sense positivity and negativity. Okay. This is called the triangle inequality. Though I don't see any triangle. Okay, I will bring all these things a little later. And I'll also, from that I will observe one more property. Suppose r and s are in any two real numbers. Okay. Now, I can write r as r minus s plus s. I subtract and add s. So therefore, mod r is mod r minus s plus s. But the modulus of a sum, the absolute value of a sum, is less than or equal to the sum of the absolute value. So this is less than or equal to absolute r minus s plus absolute S. Now take it to this side. So absolute R minus absolute S is less than or equal to absolute R minus S. Okay. Now if we interchange S and R, what happens? Absolute S minus absolute R is less than or equal to absolute S minus R, which is minus 1 times R minus S, but minus 1 times will come out as mod 1 minus 1, which is 1. So both this number and its negative are less than or equal to mod R minus S. So call this number as alpha. So alpha is less than or equal to mod R minus S. Minus alpha is also less than or equal to R minus. So therefore, what can I say about mod alpha? Mod alpha has to be either alpha or minus alpha. So both of them are less. So mod alpha is less than R minus S, or modulus of mod R minus mod S less than mod R minus S. This is a simple inequality which we will be using very often. Okay. Now you generalize this idea in a vector space, you get the notion of a norm and a norm linear space. You generalize this notion of R minus S. R minus S tells you what is the distance between R and S. R is a real number, S is a real number. The difference is precisely the distance. So if we generalize that R minus S notion, you get the idea of a metric space. So this same thing viewed from two different angles, you get the idea of a metric space, and a special case of a metric space is the norm linear space. So we can immediately generalize this idea and then see whatever proof we give using these properties of mod R, those will be immediately carried over in a norm linear space. Whatever properties we get using the R minus S properties, modulus, it will be immediately carried over in metric spaces. So that's the immediate generalization. We can see a huge amount of generalization almost parallelly going through. So what I propose to do in next class is start from this, okay, this idea, and first state the generalization, and then look at some property of real numbers, and then look at the generalization, and keep on going for real numbers and corresponding generalization. Then we'll come to functions. Okay. So next chapter will be the properties. These are called topological properties that arise out of this absolute R and absolute R minus S and their generalization. Okay. So this today we concluded the real number construction. Because I will not be available on Thursday. So the next class will be next Tuesday. Okay, I will not be available for Thursday, Friday also, so I can't compensate on Friday also. So we'll meet next Tuesday when I start with real number property.